Hi everyone, this is Yi Zhu from Fisheries and Oceans Canada. Today I'm going to present a case study that I've been working on the last couple of years, trying to use the machine learning technique to study climate change impact on Chilko Lake Sockeye salmon. First, I would like to thank all of my co-authors, Mike Hawkshaw, Cai Hongfu, David Patterson, Roy Alston, Peter Chandler, and Carrie Holt for their generous help on this project. For those of you who don't know where Chilko Lake is, it is located in the central British Columbia area, so just north of where PICES headquarters is. It is about 70 kilometers long and 3 to 5 kilometers wide, with a total area of 185 square kilometers. On the top right is a beautiful picture of the lake. Chilko Lake is one of the most important rearing lakes for sockeye salmon to spawn in Fraser River watershed. I'm going to give a short life history introduction. 4 years ago, sockeye salmon came to the lake and spawned eggs. After that, they hatched in the Chilko Lake until 2 years ago they became smolt and migrate to the ocean, and now they are coming back to spawn again. The majority spawners are 4 years old, and a small portion of returning adults are 5 years old. The reason why we chose this lake is because luckily enough, we have a long time series back from the 1940s, so we've got about 70 years of data. We know both spawners and their age proportions, as well as we know the abundance of juveniles when they leave the river and migrate to the ocean. When we started doing this project, Chilko was forecasted to be the largest stock for the entire Fraser River, which contributed to over half of the total return, and it continues to contribute relatively large proportion in recent years. In 2021, the contribution is about 43% of the total Fraser run size. Over many years, we know that our forecast model wasn't perform very well. The correlation coefficients between the forecast and the observation is very small. The current forecast model is using a very simple productivity model, which assumes the productivity is an average of the past 8 years. It was selected from a dozen models, including some Bayesian statistical models like Ricker or Larkin models, and we also considered sea surface temperature at Entrance Island, Pine Island, and the Fraser River discharge near Hope and the Pacific Decadal Oscillation. So the objectives of this project is to collect additional environmental information from both freshwater and the ocean, and then develop a quantitative predictive model to study the influence of multiple environmental variables on each specific sockeye recruits. Then to identify the key environmental variables and evaluate the model performance by comparing predictions with the available fisheries data. And last, try to update the forecast with a new method. We collected 2 types of data, the fisheries data and the environmental data. Data highlighted in red are additional data that was not considered in current forecast models. The fisheries data are the same as the forecast, except we also considered juvenile length. Additional environmental data includes river and ocean temperature, wind stress, as well as a suite of climate indices and artificial factors. We used a machine learning method, the Boosted Regression Trees model, for this study. It is a tree-based method that combines two algorithms. The traditional regression trees related a span's variable to their predictors by recursive binary split. The boosting algorithm combines all the trees by evaluating the predictive performance. There is a user-friendly R package to implement this method fairly straightforward, with the equations being the recruit is a BRT function of spawners or juveniles and the associated environmental variables. Comparing to current model, BRT has some good advantages. It is a non-parametric model, which allows more flexibilities comparing to parametric models because it doesn't assume any fixed relationship. It can handle both linear and nonlinear relationship. It can treat multiple variables at the same time. Comparing to current model, either consider no environmental variables or only one at a time. It can handle both numerical and categorical variables, such as binary variable, like spawning channel, presence or absence. It is also not sensitive to data structure, can either be normal or non-normal. It is not sensitive to outliers or scales. And last but not least, it can handle missing data. Compared to current method, we have to fill the missing data with our best guess. Here is a comparison between the observation and the BRT model for both H4 and H5 fish. As you can see, our model generally aligns with the observations for both ages. This is the fitted function, which tells us the relative importance of each predictors and their contribution. For both H4 and H5 fish are dominated by a stock recruit curve, thought like a Barrington-Holt curve, followed by effective female spawners of some environmental variables. For H4, the environmental effect is small. November discharge during adult return year and the downwelling favorable wind stress during the out-migration year contributed about 5.7% of the total variation. For H5 fish, it looks like July sea surface temperature near Pine Island, the Northern Oscillation Index, and Fraser River discharge during adult migration year are important predictors, and they contributed 13, 10, and 8% of the total variation respectively. This shows you a new forecast model. We use the BRT model to predict both H4 and H5 adult recruits on the top panel, and we combine them together on the bottom panel and compare to the previous forecast models. As you can see, the BRT model prediction isn't perfect, but it really improved compared to the previous forecast models. And this year, the preliminary in-season survey estimate is about 1 million fish, and our pre-season forecast model gave us 311,000, and our BRT model estimate is 720,000. So we are not there yet, but we are moved to the right direction. In addition, we also studied the productivity. It looks like for freshwater productivity, the smolt per spawner, they are more related to biological factors and the freshwater conditions, such as juvenile length and the abundance, and the spawning channel. For marine productivity, it is more related to marine conditions, such as downwelling favorable wind stress. So to summarize this study, we developed BRT models to study age-specific stock-recruit relationship coupled with multiple environmental covariates. We found that both H4 and H5 recruits showed a Barrington-Holt relationship rather than Ricker or Power model, which is currently used in the forecast. The environmental drivers are different for different age recruits. Generally, they play a small role. We also found freshwater productivity is related to freshwater environmental variables, and marine productivity is related to marine environmental variables. All the identified relationships are nonlinear. This result can help us understand the system better and will be useful for future forecasts, as it seems to have better performance comparing to the current forecast models. With that, I would like to acknowledge all the folks who had provided me the data and the technical support to these projects. I also would like to thank Dr. Hannah, who kindly invited me to this workshop. This project is funded by Fisheries and Oceans Canada. My colleague took this photo for me last week when we were in the field catch and release sockeye salmon. So please feel free to email me if you have any questions or comments. Thank you so much for your attention.